Hi, this is Dr. Collins Jones. Welcome to segment 6 of my video series on manual cell counting and cell density calculations. In this segment, we're going to do some additional practice problems, but the focus here is on visualizing what's happening. That is, matching the word problem to what you're actually doing in the lab. So to do that, I've created some pictures. They're not the greatest, but hopefully they'll give you the idea to show you or to illustrate the actual process associated with the words in the problem. The one thing I'm not going to do in this segment is ask you to count cells on the hemocytometer grid. We're going to assume that you've achieved proficiency with that in segment 5 and in the lab. So here in this segment, we're really going to just focus on practicing some additional problems and also looking at a few of the issues that you may encounter, especially if you're working with a new person or if you are a new person, some of the things that might go wrong with cell counting. So let's get started. Visualizing cell counting calculations. Here's our first example. A 0.50 mil sample of detached cells was removed from a T75 flask containing 14 mils of media. The 0.50 mil sample was used for counting. 50 microliters of the counting sample was diluted to 200 microliters using 1x PBS. A 50 microliter aliquot of the diluted cells, that is the cells that were diluted with PBS, was removed and mixed with 50 microliters of trypan blue. After 2 minutes, the hemocytometer was loaded and a total of 68 cells were counted over 3 squares. So I'm giving you the cell counts instead of you having to look at the hemocytometer, but you would have obtained that 68 cells by looking through the microscope and counting manually on the hemocytometer grid. 10 of the cells were blue, that is, they were not viable, they were dead. Calculate the percent viability and the total live cell concentration. Let's try then to visualize the dilution process, what we actually did in the lab before we do the calculation. So we're going to start with our T75 flask containing 14 mils of media, and in that flask are the detached cells. Remember that the cells have to be in suspension or they have to be detached in order to remove an aliquot to work with to do the counting, right? And so again, if it's anchorage dependent, we detach mostly by using trypsin. Occasionally, as a last resort, we scrape the cells, right, with a cell scraper. But the cells must be detached and they must be uniformly dispersed throughout the flask. Whether it's a suspension flask or a T flask, you have to make sure that the cells are actually floating around, they haven't settled, and they're not all clumped or settling in one part of the flask. Okay, so we have our T flask here. The cells are detached. Okay, we're going to remove a 0.50 mil aliquot, and that's just arbitrary. That's the volume that I remove when I have to count cells in the lab. So we're going to remove a 0.50 mil aliquot and place this in a pyrogen-free microcentrifuge tube. Okay, so there's our microcentrifuge tube. Okay, so we're going to remove, right? Oh, sorry. And we're going to do this aseptically inside the BSC, right? So we're going to open the flask. We're going to remove our sample, and we're going to put it into the pyrogen-free microcentrifuge tube inside the BSC so that we do not contaminate the cells in the T flask, because we're going to use the remaining cells to passage once we calculate the correct concentration. So we'll remove a sample of the detached cells, place that sample into the microcentrifuge tube. All right, and this will then be 0.5 mils of working cell suspension. So this suspension, right, the suspension right here in the microcentrifuge tube is representative of the cells in the entire T flask, and so this concentration should be equivalent to the concentration that is cells per mil in this T flask. And again, put the little blue line here to remember that we are doing this operation inside the BSC using proper aseptic technique. Okay. Now, once we have our working cell suspension, we can remove that from the BSC and begin to do the dilutions on the outside. All right. So it said remove a known volume, and it said here 50 microliters of the counting sample was removed. Okay, so we've removed 50 microliters, placed it into the next, right, into another pyrogen-free microcentrifuge tube. And there we go. Okay, and now we're going to dilute this to 200 microliters using 1x PBS. So that means that we're going to add 150 microliters of 1x PBS, right? So, and again, we know how to calculate how much to add because we want a 200 microliter final volume. We use 50 microliters of the counting sample, so 200 minus 50 is 150. Okay, so now we have our diluted cells with PBS, right? And V2 was 200 and V1 was 100. Final volume, right? 50 microliters plus 150 is 200, and we diluted 50 microliters. Now, why are we doing this dilution, right? Why do we need to do dilutions, right? The reason we need to do dilutions is we want to make sure that when we actually load the cells on the hemocytometer, we're in the proper range of 20 to 50 cells per large counting square. So we want to make sure that we're in that 20 to 50 cell range to ensure accurate and precise counting. So if we need to, we will dilute our cell suspension to ensure that we're loading 20 to 50 cells per counting square. Okay? All right, so our dilution factor here is going to be 200 over 50. Next, then, we're going to remove 50 microliters of these cells that we have diluted, all right, and dilute them with an equal volume, that is 50 microliters, of trypan blue. Okay? All right. And so remember that every time we combine the cells with either PBS or some other appropriate diluent like HBSS, and that we add the trypan blue, we need to ensure that we thoroughly mix the cells, but we have to mix gently because we don't want to put any shear forces on the cells or they'll die. So gentle mixing, we could do this by slow trituration, drawing up and down in a pipette tip, or by just gently tapping the side of the microcentrifuge tube with your fingers, right? But again, the key here is not to generate a lot of shear force to make sure we don't accidentally kill the cells. Okay, so here we've now added 50 microliters of the diluted cell suspension to 50 microliters of trypan blue, so our total volume is 50 plus 50 or 100 microliters. So again, our second dilution factor will be 100, right? V2 is 100 and V1 is 50. So our second dilution factor will be 50 over 100. Then we're going to wait 2 minutes, right, in order for the non-viable or dead cells to take up the trypan blue, but we don't want to wait too long because if we wait too long, viable or live cells may also begin to take up the trypan blue. So manufacturers recommend 2 minutes, and then we're going to load the hemocytometer, right, and count the live and dead cells. And so this is the part I'm omitting. We're going to assume that you can now successfully look in the microscope, focus on the hemocytometer, get the cells focused, and make an accurate reproducible count. So in the problem, we were given total cells of 68 cells total. There were 10 dead cells, okay? So we have 58 live cells. All right. So now that we've visualized the problem, let's solve the problem. Again, our cell numbers, total number of cells was 68. The number of live cells was 58. 68 total cells minus 10 non-viable or dead cells. And we want to keep in mind that we counted 3 squares. Remember, we said 10 is optimal, but I'm just mixing up the number of squares to illustrate how our formula to calculate cell density or cell concentration always works. Okay, let's calculate the percent viability. Percent viability is the number of live cells divided by the total number of cells times 100%. So the percent viability, this is just plug and chug. 58 live cells divided by 68 total cells times 100% gives us a percent viability of 85.3%. And again, remember that we report our final values to 3 significant figures for cell counting data. Cell density, right? Cell density is given by the number of cells per mil, which is the number of total live cells, because again, dead cells won't divide. So when we're seeding a new flask, we want to know how many cells are available to undergo cell division to proliferate, right? So cell density, cells per mil, is the number of live cells divided by the number of squares counted times the dilution factor. So here we did 2 dilutions, so there will be 2 dilution factors. If for some reason we did 3 dilutions, there will be a 3rd dilution factor there. And finally, we multiply this by the hemocytometer constant, the hemocytometer correction factor, but we multiply by 10 to the 4th. So the cell density then, if we just plug the numbers in, 58 live cells divided by the 3 squares they were counted in. So 58 live cells divided by 3 squares times the first dilution factor, 200 over 50, times the second dilution factor, 100 over 50, times 10 to the 4th. Okay, and yes, you could simplify these to 4 over 1 and 2 over 1. I always just leave it like this because when you do these in your head, sometimes you make a mistake. So I just leave all the original numbers in there and plug them into my calculator. And when you do that, you get a cell density of 1.55 times 10 to the 6 cells per 1 mil. So in every 1 mil in that T75 flask, in every 1 mil, there is 1.55 or 1,550,000 cells. Okay? All right. Now, for the next problems, what I'd like you to do is I'll put the problem up, and then I will pause for a few seconds, and I hope that you will then pause the video and try to work the problem out on your own, and then watch me do the solution. So I won't really read through the problem. I will illustrate the process and match what I'm illustrating to what you're reading in the problem. But I want you to read the problem and try to solve it on your own before you see my solution. Okay, here we go. All right, oops, sorry, and 3 significant figures. So here's example 2. So I'm going to pause, give you a few minutes to read it and another few minutes to work it out. So I'm going to count to between 5 and 10 and then resume. Okay, I'm back. Hopefully you guys tried to work this out, and let's see how you did. All right. Let's visualize the problem. We have a T25 flask containing 6 mils of media. So here's our T25 flask, 6 mils of media. And honestly, hopefully by now you realize the volume of media to solve this type of problem doesn't really matter. It will in the last segment, but it doesn't really matter here. Okay. And then it says that we removed 0.35 mils. Okay. And again, we're doing this in the BSC aseptically. So we're removing 0.35 mils, placing that into our pyrogen-free microcentrifuge tube. This will be our working cell counting sample. So once we've obtained this sample, we can take our microcentrifuge tube outside the BSC and begin the dilutions. And the first thing we see here is 30 microliters of the counting sample was diluted to 300 microliters with 1x PBS. So here's our 30 microliters, right? And it says we've diluted 2, so that's our final volume. So that means that we had to add 270 microliters of PBS, right? 300 minus 30 is 270 microliters of PBS. So our dilution factor is going to be the final volume, 300 microliters, divided by the initial volume, 30 microliters. So this is our PBS diluted sample. Now, to do the viability counting, we need to take a aliquot of this and mix it with trypan blue. So we're going to take 100 microliters of our PBS diluted sample, mix it with 100 microliters of trypan blue. And again, with means that we're going to add the two together. So now we have a final volume here of 100 plus 100 is 200 for our final volume, and our initial volume is 100. So our second dilution factor is 200 over 100. And then we did our count, right? 49 total cells, of which 22 were blue. We only counted one square. Again, this is not best practices, but that's what was stated in the problem. And a single square was counted after 4 minutes. And remember, we really should start counting after 2 minutes. So these are some of the kinds of errors that you want to look for if you're just starting to do counting or if you're training somebody to do counting. Okay, so our cell numbers again, 49 total cells. We have 27 live cells, 49 total minus 22 non-viable or dead. To calculate the percent viability, again, it's the number of live cells divided by the total number of cells times 100%. Okay, and so the viability is 27 divided by 49 times 100%, or the viability is 55.1%. Again, 3 significant figures, and honestly, this is not a very good viability. We would start to think about doing a root cause analysis to figure out why the viability is so low. All right, and some cells inherently have a low viability, but we would try to figure out why is this viability low. Did we wait too long to passage? Was there a change in the incubator conditions? What are the things that could have gone wrong? So again, when we see low viabilities, we start to get a little bit concerned. All right, let's calculate then the cell density, right? Same thing here. 6 mils of media in the T25. We removed a 0.35 mil aliquot, right? Instead of my normal 0.5. We took 30 microliters of that cell suspension, diluted it with 270 of PBS to give us our dilution factor of 300 over 30. And then we took 100 microliters of the PBS diluted cells, mixed them with 100 microliters of trypan blue to give us 200 over 100 as our second dilution factor. And again, just summarizing the data that we have, 49 total cells, 22 non-viable, 27 live, we counted 1 square. Okay, so cell density. Cells per mil is equal to the number of live cells divided by the number of squares counted times the dilution factors, of which there are 2 here, times 10 to the 4th, the correction factor for the hemocytometer. So if we plug these numbers in, right, the cells per mil is going to be 27 live cells divided by 1 square, right? And just as a check, okay, there's 27 cells per 1 square. That is between our acceptable range of 20 to 50 cells per square. Times our first dilution factor, 300 over 30, times our second dilution factor, 200 over 100, times 10 to the 4th. And so this gives us a cell density of 5.40 times 10 to the 6 cells per mil. And again, 3 significant figures. And notice that I write down the formula again for each of these problems and then plug the numbers in. It just helps to reinforce, it gives you the memory, the muscle memory, if you will, or the memorization of these formulas so that they just come to you naturally. Okay, and again, we want to solve all these kinds of problems linearly in a way that's very easy to follow. In case you get audited, the auditor can see exactly how your work goes. All right, example 3. Again, you can read through this, then try to solve the problem, and then come back and see how you did matching my solution. All right, so I'm going to count to 10, and I'm going to work through the problem. All right, I'm back. Let's see how you did. So here we have 60 mils of media in a T225 flask. And again, the presumption is that the cells are detached. Okay, so we're going to remove a 0.30 mil sample, place that into a pyrogen-free microcentrifuge tube. This becomes our working cell suspension. And again, hopefully you're thinking, yes, I did this process in the biological safety cabinet using aseptic technique. And I just have eliminated putting the little line there to save time. because hopefully you have the idea now. So from this 0.30 mil sample, right, the counting sample, I'm going to remove 50 microliters, all right, and I'm going to dilute it with, right, with 1,000 microliters of 1x tris EDTA. So you should be thinking, this doesn't sound right. But remember, these are sample problems, and I'm just trying to get you guys to think as you go through the problem. So I mixed this with 1,000 microliters of tris EDTA. And so now this is not going to be a nice number. And this could be a mistake that somebody makes. But as long as you document or record the volumes that you use, you can always fix it in the calculation, if you will. All right. So with means we added the two together. So our final volume is going to be 50, the amount that we withdrew, plus 1,000. So this is going to be 1,050 microliters as our final volume. And our initial volume is going to be 50 microliters. Okay. So even though this is a weird number, because maybe we meant to set the P1000 pipette to 950, but we didn't, right? So we accidentally pipetted 1000, but it still can be accounted for in the dilution factor. Okay, so we've done this dilution. Now we're going to do our trypan blue dilution. We're going to remove 150 microliters of our tris diluted cells, right? And we're going to mix that with, right, with 250 microliters of trypan blue. And so now our dilution factor, final volume, is 150 plus 250, 150 plus 250, which is 400 microliters. And our initial volume is 150. Initial volume is 150. All right, so now we do the count, and we got 403 total cells, 121 were blue or non-viable or dead. We counted over 10 squares. Yay, so we finally counted the right number of squares, and we counted for 10 minutes. Because notice the problem says, calculate the percent viability and the total live cell concentration. Is this count reliable? Why or why not? So let's do the calculations first and then answer whether or not we think the count is reliable. Okay, so again, just to summarize our cell numbers, total cells are 403. The number of live cells is the total cells minus the dead cells, or 403 minus 121, which gives us 282 live cells. Okay. Percent viability then, number of live cells over the total number of cells times 100%. So this is going to be 282 live cells divided by 403 total cells times 100% gives us a viability after we round this up, because when you did this on your calculator, it was like 69.99%, and we can only have our three significant figures. So the viability, we round it up to be 70%. So we observe the rules of significant figures. Okay. Cell density, cells per mil times total live cells divided by the number of squares counted times the dilution factors times 10 to the fourth. Okay. So cell density is going to be total live cells, 282 divided by 10 times 1,050 divided by 50, right? That's perfectly fine. Times 400 over 150 times 10 to the fourth. Okay. And when we do that calculation, we get 1.58 times 10 to the seventh cells per mil, again, observing three significant figures. Okay, so we've calculated percent viability. We've calculated the cell density. Is this count reliable? Why or why not? And so you're looking here for things that were not following the SOP, where the procedure, the specified procedure, was not followed correctly. And so the answer is this count, in my opinion, this count is not reliable, right? The count is not reliable. One, we diluted it with tris EDTA. And while tris and EDTA are commonly used in biotechnology, biochemistry labs, right? It is not, tris EDTA is not a balanced salt solution. So the osmolality will be incorrect, and that may cause the cells to die because the osmotic pressure inside and outside is not the same. So we did not use the balanced salt solution, so that's one huge error. Okay? In our lab, our SOPs say that you need to use equal volumes of cells and trypan blue, and here we did not. Right? We used 150 microliters of cells and 250 microliters of trypan blue. Those are two different volumes, so this is not a 1-to-2 dilution. So we should have used the same volumes. Now, if your SOP says, use as much trypan blue as you want, that's fine. But our SOPs say equal volumes of cells and trypan blue. We waited 10 minutes, right? After 10 minutes, the hemocetometer was loaded. That is a long time for cells to be sitting in trypan blue. So it is likely that at least some viable cells took up the trypan blue. So some cells that were alive, because they sat in the trypan blue for so long, took up trypan blue. So again, timing, according to manufacturers, is important. And then the last thing we might look for is, do we have the correct range of cells? Are we within that 20 to 50 cells per square? And it turns out that we are, right? We have approximately 38, more than 38 live cells per square. Okay, sorry. So that was a mistake. Really, we did 10 squares, 403 total cells. So 403 divided by 10 is roughly 40 cells per square. All right, so that's not bad. Okay. Last example, same thing. Please read through this. Please try to work the problem on your own and then come back and see how you did. I'm going to count to 10 and then resume talking. Okay, let's see how you did. Again, I like to illustrate the problem. It just helps me keep track of everything. So here I have 12 mils of media and a T150. That seems a little bit not enough media, but that's what the problem stated. Okay, we removed 0.75 mils. And again, you notice I've changed the volume of the aliquot that we're removing because it really doesn't matter how much of a cell suspension we withdraw to do our counting, just so we have enough. So it could be 0.3, 0.5, 0.75. And again, I typically use 0.5, but it could be a different value, whatever works for you. So we've put that into our pyrogen-free microcentrifuge tube. From that, we're going to remove 25 microliters from this tube and place it into a new pyrogen-free microcentrifuge tube and dilute this to 1,000 microliters with Wi-Fi water, right? Water for injection. All right, so the final volume is 1,000. And that means that we added 975 microliters of Wi-Fi water, right? Because it's 1,000 minus 25 is 975. So our dilution factor will be 1,000, the final volume, divided by the initial volume, 25 microliters. From this, we removed 50 microliters of the diluted cells, okay, and mixed it with 150 microliters of trypan blue. So this is going to be 50 plus 150, right? 50 plus 150 to give us a final volume of 200 microliters. So V2 is 200 and V1 is 50. And then we summarize our cell counts. We counted 719 cells over 10 squares. So you're already thinking this is roughly 72 cells per square. So that's not good. 115 cells were dead, right? Were blue. They were non-viable. And we counted, again, 10 squares. Yay. So we did that part right. But it took us 10 minutes before we loaded the hemocetometer. So all of those could be problematic. Okay, so again, cell numbers. Total cells, 719. Live cells, 604, right? 719 minus 115. Okay, and so percent viability, live cells divided by total cells times 100%. This will be 604 divided by 719 times 100%. This gives us 84% viability, which is not bad for all the mistakes that you might have noticed were made during this counting. It's probably not really the way it would come out in real life, but this is a sample problem. So that's our percent viability, 84%, 3 significant figures. Cell density. Again, cells per mil is equal to the total live cells divided by the number of squares counted times the dilution factors, there are 2, times 10 to the fourth, the hemocytometer constant. Okay? And so the cell density is, again, 604 live cells divided by 10 squares times 1,000 over 25 times 200 over 50 times 10 to the fourth. Okay. So we plug the numbers in, we get 9.66 times 10 to the 7th cells per mil. Again, obeying our 3 significant figure rule. And again, this count would not be considered reliable. Even though we got a pretty good percent viability, we diluted with Wi-Fi water, right? So again, we're not maintaining the correct osmolality, and that means that the cells will be under osmotic stress and likely will die. Again, we did not use, at least according to the SOPs that we use, we did not use equal volume of cells and trypan blue. Again, we waited 10 minutes. That's too long, right? We waited 10 minutes before we started our count, and we have almost 72 cells per square. So we're outside the acceptable range of 20 to 50 cells per square, which means we probably made an incorrect count. We either double counted some cells or we missed counting some cells incompletely. So that means that we need to make this sample even more diluted. Okay, and in the previous segment we told you how to estimate that. All right, and that is the end of segment 6, the next to the last segment.